All right, welcome back. This video is for the second learning target of our unit, and it begins on page 5. Go ahead and turn to page 5. Learning target today is I can identify what a function is. So the lesson before this, we had talked about definition of what a function was. So today we're going to identify if a specific table, a specific equation, or a specific graph is actually a function. Okay? So let's quickly review what a function actually is. What is a function? So previous lesson to this, there are two important pieces here that made something a function. A function is a function when each input has exactly one output. And remember, the input is the x, and the output is the y. Okay? So remember the function machine. If you put in an input, only one output will come out. Okay? So each input has exactly one output. Another characteristic is, we're going to keep bringing up here, this one's to come out. In a function, the y depends on the x. Okay, so the y is dependent on the x. So let's just review from yesterday. Examples of functions and non-functions. Will you go ahead and pause the video and see if you can come up with a table, an input-output table that represents a function, and an input and output table that represents not a function. And then you can unpause and we'll talk about it. Okay, let's take a look. So remember, a function and a table, I can come up with any inputs here. So I'm going to come up with 2, 3, 4, and 5. And let's say all my outputs were 1s. This is a function because each one of these inputs are different and they each have one output. Okay, so this is a function because each input has one output. And it's okay that they all have the same output because they come from separate inputs. So keep in mind, if I put a 2 in the machine, out comes a 1. Put a 3 in the machine, out comes a 1. It's okay because only one output is coming out for each one of those inputs. So for not a function, if we look at this, let's say I had 3 inputs and they're all 1s, and then my last one was an 8. And the outputs were 3, 4, 5, 6. Well, this is not a function because these 3 inputs, they're all the same input, they have all separate outputs. So this is not a function because the input of 1 has 3 different outputs. Okay, has 3 different outputs, which breaks the rule of each input has exactly one output. Meaning if we go back to this function here, this function machine, if I put a 1 in here, out's going to come a 3, a 4, and a 5. And that breaks the rules because each input has to have one output. Okay? So, example of a function, example of not a function. Okay, and yesterday, or the previous lesson, we also talked about different labels that create functions. Okay, so this is where the y depends on the x. Can you give me a label for a y, which is dependent on the x? 2 variables that have a relationship that y depends on the x. Can you give me a y and an x where y doesn't depend on the x? Then it's not a function. So examples that we talked about yesterday that you may have come up on your own is, if I said money made is the y and hours worked. These 2 variables have a relationship that create a function because the y depends on the x. The amount of money that you make at work depends on how many hours you have put into work. Okay, so you work 1 hour, you make so much. You work 2 hours, you make more. Work 3 hours, you make even more. If we look at a non-example of not a function, let's do y is hair length. And let's say x is age. Whoops, age. Well, this is not a function. This is under the not function because y does not depend on the x. The hair length does not depend on how old you are because you could have a 2-year-old with long hair and you could also have a 10-year-old with the same amount of, a 2-year-old that has really short hair. Okay, so again, the hair length does not depend on age. All right, let's take a look at how do we tell if an equation is a function. So the key here today for equations is you have to make a table in order to tell if a equation is a function. So we're just going to make our simple xy table, our input-output table. Let's take a look at the first one, y equals 2x plus 1. We're going to make an input-output table, xy. And let's just go with defaults of -2, -1, 0, 1, and 2 for our inputs. And let's complete the table by inputting each one of these inputs into our x so we can see what our output is. So I'm going to start on the positive end. If I put a 2 in for the x, 2 times 2 is 4, 4 plus 1 is 5. Put a 1 in, 2 times 1 is 2, 2 plus 1 is 3. Put a 0 in, it's going to equal 1. Put a -1 in, 2 times -1 is -2. -2 plus 1 is -1. Put a -2 in, this will equal -3. So if you look at the table, does each input have one output? Yes, it does. So according to our table, y equals 2x plus 1 is a function. Yes, because each input has one output. Okay, well, you go ahead and just pause this video and go ahead and graph this table on the graph that's given. Okay, this is what your graph should look like, and you can see that it is a linear line, it's a straight line. Let's try the second equation, y equals x squared. So again, we're going to make a input-output table here, xy table. Let's use the same inputs we used previously, -2, -1, 0, 1, and 2. And let's go ahead and input each one of these x's into our equation x squared and see what the output is, the y. Let's start with the positive 2. I always like to start with the positive. If I put in 2 into my x, 2 to the second power is 4. Put in 1, 1 to the second power is 1. 0, 0 to the second power, 0 times 0 is 0. -1, if I put a -1 here, -1 to the second power, so in other words, -1 times -1 is +1. -2 squared, -2 to the second power is -2 times -2, that's a +4. So does this table represent a function? Does each input have one output? Yes, it does. Y equals x squared is a function because each input has one output. And I realize, yes, that we have two outputs that are 4s, two outputs that are 1s, but they each come from separate inputs, so that is okay. So yes, this is a function because each input has one output. All right, so go ahead and give this video a pause. See if you can graph y equals x squared. Plot the 5 ordered pairs from your table and see what the graph of y equals x squared looks like. Okay, this is what your graph should look like. It's a U-shaped graph. I know some people think it's a V-shaped graph, but it is a U-shaped graph. This is a type of graph you're going to learn later on in the year. This is called a parabola. So y equals x squared. Yes, it's a function because each input has one output in the table. Last equation, y equals the square root of x. Is this equation a function? So let's go ahead and make an input-output table. This one I'm going to specify a certain set of inputs for you. Okay, so we're not going to go with -2, -1, 0, 1, and 2. We're going to specifically go with 0, 1, 4, 9, and 16. And the reason why is because, remember, you can't find the square root of negative numbers, so we don't want negative inputs. And I'm going to pick perfect squares so we don't have any decimals. Okay, so let's give this a try. If I input a 0 into my x, the square root of 0 is 0, so we're good. If I input a 1, the square root of 1 is 1. But remember when we talked about square roots, every square root has both a positive square root and a negative square root. So if I also put in a 1 into this x here, the square root of 1 also equals -1, okay? If I input a 4, the square root of 4 is 2, but the square root of 4 is also -2, okay? Square root of 9 is 3, but it's also -3. And if I put a 16 in here, square root of 16 is 4, but it's also -4, okay? So according to our input-output table, is y equals square root of x a function? This one is no. This equation is not a function because each input actually has two outputs here. The input of 4 has two outputs, 2 and negative 2. The input of 16 has two outputs, 4 and negative 4. So no, each input except 0 has two outputs. Breaks the rules of each input has to have exactly one output. Okay? I'm going to challenge you here. Give this a pause. See if you can graph this. You're not going to be able to fit every single point on this. You're most likely only going to be able to fit these 3 on your graph. And then unpause and see if you graphed it correctly. Okay, this is what your graph should look like. So just in case you got confused, 0, 0, there's the origin. This one has two ordered pairs, so 1, 1. 1, 1 is this dot right here. And then 1, negative 1. So 1 and then negative 1. These two dots right there represent that second set. 4, 2, and 4, negative 2. So 4, 2, and 4, negative 2. So again, you're going to notice it's another U-shaped, but it's sideways this time. So it's a little bit, it's a flipped version of the one right above it. So this one is not a function. Keep that in mind because each input has actually has two outputs. It doesn't have exactly one output. Okay, go ahead and flip the page here. So now that we've seen how to tell how an equation is a function by making a table, how do you tell if I were to give you a graph if it's a function or not? In this method, in this part, you're going to use the method of something called the vertical line test. Okay, so what that means here is, I'm going to start with something that you already know. So I have this graph and I want to know if it's a function. Okay, and the easiest way to tell is you can make an input-output table. This is the longer route. So in other words, you have to pick some points that you want to put on your table. So let's see, I'll pick 4 points here. Here's a point. Let's use this point. We could use this point and this point. And if we write these ordered pairs in our input-output table, first pair is 0, 2. Next pair is 1, 2, 3. And then it went up 1, 2, 3, 4, 5. So that's the ordered pair 3, 5. This one right here is 1, 2, 3, 4, 5. And up 2.5 it looks like. And the last one, 1, 2, 3, 4, 5, 6, 7, 8, and 1. Okay? According to the 4 ordered pairs, does each input have one output? It doesn't look like I have multiple outputs. So yes, this one, according to the table from the ordered pairs I picked out from the graph, represents a function. Well, what the vertical line test shows is this. And this is the easier way to do this. If you can draw a vertical line everywhere on this graph, anywhere on this graph, it only passes through your vertical line once. Now keep in mind a vertical line is straight up and down. Okay, so anywhere I draw a vertical line along this graph, it always just passes through my vertical line one time. Okay, so this vertical line the graph only passes through that point. And this vertical line, it only passes through that point. This vertical line there. This vertical line there. That means you can't draw a vertical line anywhere on this graph that passes through it more than once. If it follows that rule, then you know that it passes the vertical line test, and it is a function if it passes that test. So this one is a yes, because it passes the vertical line test. Every vertical line you draw along the graph, it only passes through it one time. Okay, so we can write yes. Whoops. Okay, we're back, sorry. We're going to write yes, it passes the vertical line test. Okay, let's take a look at the second graph. Let's start out by doing it the long way. Let's make an input-output table. So I'm going to pick some points on this graph. How about here, and here, and here, and here. Okay, so let's take a look. This ordered pair right here is 0, 3. This ordered pair right here is 1, and it's almost 3. Let's just say it's 2.8. This point right here is 1, and it looks like it's also almost down to 3, so negative 2.8. And this ordered pair here is 0 and negative 3. Well, according to our table here, does this represent a function? No, it doesn't, because, take a look, this one single input, a 1, produces two separate outputs. Breaks the rules. Even this one, 0 and 0, the same input, but they each come out with separate outputs. Okay, let's try the vertical line test. Is there anywhere on this graph where I can draw a vertical line and it passes through more than one time? Well, yes. If I draw a vertical line here, notice it passes through here and here. Fails the vertical line test. Draw a vertical line here, passes through here and here. Failed again. Line here and here, or dot here and here, failed it again. Draw it right here, passes through here and here, fails again. So this graph of a circle is not a function because it fails the vertical line test. Okay, so in other words, the vertical line test, in order to pass it, must only pass through once. Okay, it only can pass through the graph once. So that's the vertical line test. That test only works on graphs. Keep that in mind. All right, last problem. This is just a problem solving. This is a word problem that represents a function. Let's take a look at it and see why it's a function. It says, suppose it starts snowing steadily at noon. The snow falls for the rest of the afternoon at a rate of 0.5 inches per hour. Okay? X is the number of hours since noon. Y is the amount of snow that has fallen since noon. Part A, can you explain why y is a function of x? Why is y a function of x? Why is this a function? Well, remember we talked about if this is a function, the y depends on the x. So let's ask ourselves, does the y depend on the x? Does the amount of snow that has fallen since noon depend on how many hours it's been since noon? Well, yes. Of course, because it starts snowing steadily, meaning it's snowing at a constant rate since noon, and it keeps falling for the rest of the afternoon at a rate of 1/2 inch per hour. So we're going to write, explain why, because the y, which is the amount of snow, depends on x, which is the number of hours. The amount of snow depends on the number of hours that has been falling. So if it's only been an hour, there's only going to be so much snow on the ground. If it's been 10 hours, there's going to be more on the ground. Okay, B, let's write an equation that represents a function. So this one we haven't quite reviewed yet. This is coming up, but I'll help you out here. This equation is going to come in y equals mx plus b, m being the slope, which is the rate, b being the starting amount, which is the y-intercept. Okay, so we already know our rate. It's falling at a rate of 1/2 inch per hour, so this is our m, which is 1/2 inch. B, it looks like it didn't start until noon, which means that there was no snow on the ground to start with. It doesn't say that it started with 5 inches of snow. So in other words, our b is 0 because there is no starting amount. So final equation, just put the m and b where the m and b are here. And our equation is 1/2 equals 0.5 times x. And the b is already 0, so we don't need it. So here's our equation. 1/2 inch for every hour is the amount of snow. Okay, looks like we're going to graph our equation here. And we need to make a table in order to graph our equation. So let's go ahead and make an input-output table. Input-output. Remember, x's here is the number of hours since noon. So let's do 0. Because we're going by halves, let's go by 2's here. 0, 2, 4, 6, and 8. Let's see how much snow is after each one of these hours. So at 0 hours, 0.5 times 0 is 0. 2 hours, 0.5 times 2 is 1. 4, 0.5 times 4 is 2. 0.5 times 6 is 3. And 8, 0.5 times 8 is 4. Go ahead and give this table, or put these points on the table onto the graph. And then you can unpause and we'll do a summary. Okay, this is what your graph should look like after you plotted all these points. Remember, the x represents hours since noon. The y-axis is amount of snow. When you plot it, you can see that the snow is steadily rising as the hours go by. Okay, this is a function here. You can tell because I can draw a vertical line anywhere through this graph, passes the vertical line test here. You can see in the table, each input has one output. Okay, let's go ahead and close with a summary here. For summary, remember a function has exactly one output for each input. Okay, in other words, you can word it as each input has exactly one output. Second, in order to tell if an equation, if I were just to give you an equation and asked you if it's a function, you got to make an input-output table. Okay, so like the 3 examples on page 5 you can refer to. And lastly, how do you tell if a specific graph is a function? Well, you can either A, make an input-output table and see if each input has one output, or you can use the shortcut method, the vertical line test, draw a vertical line anywhere on the graph. If it always passes just through the vertical line one time for each vertical line you draw, it passes the test, it's a function. If you can draw a vertical line anywhere in the graph that passes through it more than once, it fails the vertical line test, it's not a function. Okay, go ahead and turn to page 7 and you can get started on your classwork. Keep in mind, a lot of yes/no questions here, so you must explain your answers. You have to explain your answers, why you put yes or why you put no, in order to get credit. And then check back with your answers and ask any questions. All right, good luck.